Hey class, welcome back. Let me start by reminding you that last time you met the subgroup generated by an element lowercase g inside of a big group capital G. And in general, the subgroup generated by an element is going to be a subset, or in fact a subgroup inside of G. But it can sometimes happen that the subgroup generated by some particular element is all of G. And cyclic groups are the name of the phenomenon when this happens. So namely, we'll say that a group capital G is cyclic if there exists some element, some lowercase g in that group, such that the subgroup generated by lowercase g, it's not just a subgroup, it's actually all of capital G. So let's look at some examples of familiar groups we've seen that actually satisfy this property. First, I claim that the set Z5, so the numbers 0, 1, 2, 3, 4, which we'll view as a group under addition modulo 5, I claim that that group is cyclic. And why? Well, for instance, I could try calculating the subgroup generated by 2, which remember starts with the identity, so that's 0, and then it includes 2, it includes 2 plus 2, which is 4, 2 plus 2 plus 2 in this case, since we're working mod 5, is 1. I add on another 2, and it becomes 3. And then at that point, if I were to add on yet another 2, I'd get back to 0, which I've already included. But at this point, I see that the subgroup generated by 2 contains every element of Z5, so that's enough to show that Z5 is cyclic. But 2 isn't the only element in Z5 that has the property that if I take the subgroup generated by it, I get all of Z5. Maybe a more natural choice would be to look at the element 1. If I take the subgroup generated by that, it'll contain 0, 1, and all the things I get by adding 1 to itself repeatedly, which are 2, 3, and 4. So again, that's all of Z5, and so we've seen in a different way that Z5 is cyclic. In fact, what's nice about looking at the subgroup generated by 1 in that last example is that it shows you there wasn't really anything special about the number 5 when we were looking at Z5. In fact, Zn is cyclic for any n, because no matter what n is, I can look at the subgroup generated by 1, and it'll contain the identity, which is 0, it'll contain 1, and all of the things I get by adding 1 to itself repeatedly, which will gradually give me every element of Zn. So I've found an element such that the subgroup generated by it is the whole group. That shows that this group Zn is cyclic. One other cyclic group we've met so far is the group U4, which consists of the complex numbers 1, -1i, and -i. That's a group under multiplication, and I claim it's a cyclic group. To show that, I should find an element inside of U4 such that the subgroup generated by it is everything. And if you try some different elements, you'll eventually find that the element I works. Because if I calculate the subgroup generated by I, it'll contain the identity, which is 1, the element I itself, I squared, which is -1, and I to the third power, which is -i. So I've now hit every element, meaning the subgroup generated by I is all of U4, and that shows that U4 is cyclic. Lots of the groups that we've met in this class, however, haven't been cyclic. So as a specific non-example, we could consider the symmetric group S3. I claim that group is not cyclic. To try to convince myself of this, I can start picking specific elements of S3 and calculating the subgroup generated by them. So for instance, maybe I'll start with the element 1, 2. If I calculate the subgroup generated by that, it consists of just the identity and the permutation 1, 2 itself, which is a subgroup of S3, but it's not all of S3. So that one doesn't work. That one's not something where the subgroup generated by it is everything. But maybe that's just because 1, 2 was a bad choice. So then I can pick something else, like maybe 1, 2, 3, calculate the subgroup generated by that, and what you'll find is that it'll still be a subset of S3, but not the whole thing. And so you can go down the line in this way and see what the subgroup generated by any element of S3 is, and what you should find is that you never get the whole thing. So you'll carry out the rest of that computation on your worksheet for today, and that'll confirm that S3 really isn't cyclic. So now that you have an idea of what cyclic groups are, let's ask, why is this a good thing to study? So why care about cyclic groups? Here's one reason. We've talked a bunch in this class about orders of elements in groups, but in general, computing orders of elements in groups is kind of hard. Like, it takes a lot of computation. We have to take the element and start raising it to powers and raising it to powers and waiting till we get the identity. That takes a lot of work, but there's 2 specific cases in which we have a formula that lets us calculate the order of an element in a group without doing all that work. One of those cases we've met already, that's the symmetric group, where we have this formula that says the order of an element G in the symmetric group is the LCM of the lengths of the cycles in G. And the other situation is cyclic groups. So if you have a cyclic group capital G, that means that you know that it's equal to the subgroup generated by some particular element lowercase g. And that means that every element in capital G is of the form lowercase g raised to some power. So if I want a formula that will tell me what the order of any element in this group is, what I need to do is I need to be able to tell you what the order of any power of this specific element lowercase g is. And well, I don't want to ruin the surprise quite yet, but this is where we're headed this week, is we're going to find a formula that lets us calculate in this way the order of any element in a cyclic group. So that's one reason why cyclic groups are a helpful thing to study. The last thing I want to do in today's video is tell you about one special case of this formula, which is the case where this power k is equal to 1. In other words, I want to give you a way to think about the order of the element lowercase g that generates our cyclic group. So I'll state that in the form of the following theorem. Let's let capital G be a cyclic group, which means that capital G is equal to the subgroup generated by some particular element lowercase g. Then the statement is that the order of that element lowercase g is equal to the number of elements in the group capital G. We'll prove this theorem next class, but for now I just want to conclude by illustrating it in a couple of examples to hopefully make it feel believable. For instance, I could take the cyclic group Z5, which we started with, and we noticed when we first started that Z5 is equal to the subgroup generated by the element 2. And if I calculate the order of that generator 2, I'll find that its order is equal to 5. And the way to see that is to take 2 and start adding it to itself over and over again. You'll find it's not until you've added it to itself 5 times that you get the identity. But what else is 5? 5 is the number of elements in the group Z5. So that's a special case of this theorem. The order of the generator is the same as the number of elements in the cyclic group. Something similar happens in our other example, which was U4, which we saw was equal to the subgroup generated by the element I. If I calculate the order of that element I by raising it to powers over and over again and waiting to see when I get the identity, I'll find it's not till I raise it to the 4th power that I get the identity, so its order is 4, which again is the same as the number of elements in the group U4. So that again exhibits this theorem. So we'll do some more practice with cyclic groups on your worksheet for today, and then we'll prove this theorem in the next video. So I'll see you then.